through Schultz from Williams College, and we're happy to have him speak for us on Galois module structure of p to the power of s power classes of a field.
Great. Well, thank you very much for the introduction and indeed for the invitation. I was really delighted to have a chance to talk in this seminar, and in particular talk about this project, which I have a lot of affection for, and is one that that I hope that you find interesting as well. So let me start at the beginning. Well, first, let me see if my computer will let me scroll through slides. Oh, there we go. Okay. So this is a project that I worked on collaboratively with Jan, who is in the audience today. Jan, it's great to see you. Jan, I love this picture of you because I think it captures everything there is to know about your spirit, which is fantastical and wonderful and incredibly inviting and warm and friendly. So I had the good fortune to work on this project with Jan, together with John Swallow. John Swallow was a professor at Davidson College when I was an undergraduate a number of years ago. And this particular project is an outgrowth of a project that I worked on with John and Jan as my senior thesis project. And that project has just sort of like ballooned into more and more directions. It's really been a wonderful project to work on. And because I got pictures of John and Jan, I felt like I should have a picture of me. This is a picture of me when we started working on this project. So we started on this quite a long time ago. And fortunately, my sense of fashion and style has changed dramatically in the meantime. So, all right. So first, some background. I'll start with some content that I'm sure that everyone feels happy to see, and that is Kummer theory, which for our purposes, I'm just going to focus on the case where our field has a primitive p-th root of unity. And the name of the game is to try to study the extensions of K, whose Galois group is elementary p abelian, which is to say a direct sum of Z mod PZs. And Kummer theory tells us that in the presence of this p-th root of unity, understanding those kinds of extensions is quite simple. It essentially comes down to some linear algebra. We've got a FP space, which is the non-zero elements in K modded out by those elements that are already p-th powers. And it's the subspaces of that space that classify the elementary p abelian extensions of K. And indeed, this works quite nicely with dimension and so on. So like a two-dimensional subspace corresponds to Z mod P plus Z mod P extension, right? So the correspondence is quite lovely. In essence, what it tells us is that when you've got the roots of unity, the easiest way to make Z mod PZ extensions is the only way to make Z mod PZ extensions, right? And so in some ways, the sort of birth of this project and others that are like it is to ask what happens when we take the thing I'm calling J1, which is p-th power classes. What happens if we take J1 and we assume that J1 has some additional structure besides just being an FP vector space? And when I say additional structure, I suppose the most natural kind of structure to imagine is the structure that arises when K is an extension of a field F, and there's a group, a Galois group, that then acts on the elements of K. So what happens when we take this FP structure on K and we allow this Galois action to come into the picture as well? What can we say about the module theoretic things that show up? Now, the nice news is that these p-th power classes have been studied quite extensively in the case when the Galois group in question is a cyclic p group, so Z mod P to the NZ. This started with John and Jan many years ago, where they studied exactly this question in the case when n is equal to 1. It is on the heels of that project that I joined in the fray, and we started studying this question in the case when n is something other than 1, so 2 or 3 and so on. And in studying these p-th power classes and their module structure, we've gotten a lot of interesting information that we've been able to capture about how certain p groups behave as Galois groups. So for example, anytime that you've got a submodule of the p-th power classes under this particular action, of course, that submodule is a subspace, so it corresponds to some elementary p abelian extension of K. But because it's a module, it's a real deal submodule, that extension is not just an elementary p abelian extension of K, but in fact, it's an elementary p abelian extension of K, which is additionally Galois over the base field F. And indeed, the Galois group that arises when you think about that larger field extension gives us a way to study short exact sequences that are sandwiched between these elementary p abelian groups and these cyclic prime power groups. So we can study embedding problems by looking at the structure of these Galois modules. As a consequence of that, one of the things that becomes true is that if you wind up seeing interesting module theoretic behavior, that interesting module theoretic behavior translates into interesting Galois theoretic behavior as well. And in particular, if the appearance of some kinds of modules forces the appearance of other kinds of modules, then that gets translated into what we call automatic realization results, which is to say...
Sorry, Andrew, could I
Yes.
just interrupt you? I want to make sure I'm not confused about the notation. So F is your ground field.
Yes.
Then you have a cyclic extension K of that.
Yes.
And then you're looking for a P extension of that. Is that right?
Well, what we're doing is we're taking that top field K and we're thinking about, all of the elementary p abelian extensions of that top field K.
Yeah, got it.
And what we're interested in is, of course, not just the fact that the Galois group of that field over K will be a direct sum of a bunch of Z mod PZs, but really how that also interfaces with the Galois structure that happens below that. Does that make sense?
Yep, thanks.
Okay, great, perfect, thank you. And for anybody else, please feel free to interrupt if you've got questions. I'm always happy to. In fact, it's very nice to be able to resolve these kinds of things on the fly instead of waiting to the end. Great. So as I was saying, these sort of module theoretic instances where one module forces the appearance of another module turns into an example where the appearance of some Galois group forces the appearance of another Galois group. Now, good old-fashioned Galois theory tells us that that happens a lot if what you're holding on to is, let's say, a quotient or something like that. But you can get some really interesting automatic realization results as well along these ways. And parallel to that construction is the question of counting the number of extensions of a given field that have a prescribed Galois group within some fixed algebraic closure, right? So all these questions about how certain Galois extensions arise, how they're related to each other, and the multiplicity with which they arise can all be unlocked by understanding the structure of this particular module itself. Now, the really exciting thing, of course, is that all these things are just sort of a manifestation of properties that some absolute Galois group has. And so every time that we see this kind of interesting behavior, what we're really seeing is the appearance of sort of additional structure that shows up in these absolute Galois groups. And of course, that's quite exciting because it would be fantastic to understand absolute Galois groups in a very clear way. This is a very tough problem. So what we're seeing here are some examples of how we can glean some information from those really interesting groups. I suppose the moral of all this is that when we studied the structure of p power classes in this example where we have a Galois group that's cyclic acting, the structure of those p power classes is way nicer than you would expect if what you were picking up was some random module over this group ring. And the fact that those p power classes have a much nicer structure is really a reflection of the fact that absolute Galois groups are not random profinite groups. They are profinite groups that have to play by some rules, right? And so we're getting some information about that that's getting encoded in the module structure of these p power classes. All right, so that's kind of history, so to speak. That's stuff that we've thought about before. So I want to give you two quick examples of how some of this stuff shows up in a fairly concrete way. So P is going to be a prime bigger than 2 because, of course, as I've told my abstract algebra students this semester, 2 is the oddest prime, right? It always is the place where we see some strange behavior. And for a group G in a field F, we're going to let nu of GF just count the number of extensions of F that have Galois group G, again, within some fixed algebraic closure. To give you a sense of what the module decomposition that we already calculated tells us, here's a theorem that tells us if we're interested in counting the number of extensions of F whose Galois group is MP cubed. Here, I'm using MP cubed to stand for the non-abelian group of order P cubed that is exponent P squared. So there are two non-abelian groups of order P cubed. One of them is exponent P and one of them is exponent P squared. MP cubed is the one that is exponent P squared. The point is, the number of extensions of F that have that Galois group can be computed very precisely in terms of a multiple of the number of extensions of F that have the other non-abelian group of order P cubed, plus some correcting factor that's connected to extensions of F that don't embed inside of a certain kind of extension. I don't want you to look at this theorem and feel like you have to understand everything that's on the slide. But again, what I want you to sort of be convinced of is that when it comes to doing specific enumeration questions, this module theoretic language allows us to make some really nice connections between the appearance of some kinds of groups and the appearance of other kinds of groups, all in the language of what is essentially linear algebra, right? So this is a fairly nice example of what we're seeing. And in fact, as a corollary of this, of course, if you look at this theorem, if I tell you that there is a field F and that field F has an HP cubed extension, so the number on the left-hand side of this expression right here, this number is at least 1, well, that makes the overall sum also at least p squared minus 1, which is greater than 0, which means that MP cubed had to appear as an extension as well, right? So we get a corollary that says, if your field admits an HP cubed extension, then it also has to admit an MP cubed extension. So in the language from the last slide, this corollary is what we would call an automatic realization result. It's kind of a non-obvious fact about how Galois groups appear. And it's connected to this realization multiplicity result, which is about how many times these things actually wind up appearing. All right? Does it seem okay? Okay. So what can we do from here? There are a lot of places you can go based on the decomposition for pth power classes that we already studied. And one of the things that might be natural to ask is whether we can get a more granular view of what's happening, so that instead of understanding pth power classes, maybe we could understand p squared power classes or p cubed power classes, right? And so that's the big question. We'll continue to assume that k over f is cyclic of degree p to the n. And what we would like to be able to understand is the Galois module structure of what I'm calling JS, the p to the sth power classes. We've already done this for J1. We would like to be able to do it for some more granular versions of this as well. And I'll just say right off the bat, then the big question in some sense is whether there's any hope at all that this module could be nice. And things are not looking great for us because from a purely representational, modular representation theory point of view, the ring over which we're looking at modules, as long as S is bigger than 1 and N is relatively large, like N is bigger than 1, the representation theory is a disaster. It's wild, and we don't really have a hope of classifying what the N decomposables look like. And so it's a little bit of a leap of faith to try to do this, because we are not in a situation where the context of the problem assures us that maybe something nice will happen. In fact, we probably shouldn't expect that anything nice happens. At best,
are we assuming anything about p to the s roots of unity in K or anything like that?
We're going to continue to assume that we have a pth root of unity at least, but whether or not we have higher roots of unity we'll see later that shows up in the structure that appears. But yeah, we're going to continue. Technically speaking, we've done the problem also when there aren't pth roots of unity. The only downside to that is that when there aren't pth roots of unity in play, it's not classifying the same kind of thing. Some of the motivation sort of falls apart. So we don't need to assume it, but if you want to keep telling the story that it's related to some stuff, it's more natural to think about happens when you do have roots of unity in play. So we're going to hope that maybe, not that this is nice, but maybe we can at least hope that it's understandable. So let's cross our fingers and see how it goes. Here's the general setup. Again, we're going to assume P is a prime that's at least 3. G is our shorthand for the Galois group. As before, it's cyclic of order P to the N. I'm going to let sigma be a generator of that group. Here's the graph. So K over F is the extension and G is its Galois group. Ki is going to be the intermediate field that's degree P to the I over F. So of course we get one of those for every value of I between 0 and N. We're going to let Gi be shorthand for the Galois group of that sort of quotient extension, Ki over F. It turns out that writing Z mod P to the SZ Galois Ki over F is just a bummer. So we're going to write that as R sub S, G sub I. I think the S is meant to be lowercase. Sorry, that's the first of, I'm sure, many typos. And then, so the S is keeping track of sort of how granular we are, and the GI is telling us where we are along this tower in terms of groups. And by convention, I said Ki is the extension of degree P to the I. We'll see later on, there's a reason to want to define something that we'll call K minus infinity. And this is going to be the set that only has 1 in it. It will also be convenient for us to shift into additive notation, even though when we're looking at these pth power classes or p to the s power classes, multiplication is really how we do these things. It just
Sorry,
turns out.
do you mean g sub minus infinity is 1?
Say it again?
Do you mean the g sub minus infinity is 1 or k
No,
sub
I mean
minus
k minus infinity. So all the other k's are actually fields. This is this one element that has only the number that, you know, the field element 1 inside of it. It's to make some of the other notation behave. We're going to see that there are some things that sort of drop away, and this is the right way to encode that they drop away, essentially. I agree. It looks a little bizarre right now. Like I said, we'll shift to additive notation only because if you try to do everything in the exponents, then you have to get your magnifying glass out pretty fast. So, all right. To make sense of this, I want to think a little bit about cyclic modules and how we can depict them. So gamma is a random element in the field. And when I put brackets with a sub s, what I mean is the p to the s power class that's represented by gamma. And so we can look at the module that thing generates. And if you look at the module that it generates, you can think of it in some sense as kind of like, this is the wrong way to say it, but these are sort of like FP combinations of these kinds of elements. It's not really FP, it's the elements between 0 and p minus 1. You could also think of this as almost like a p-adic expansion of sorts. But the way that I think about it is more pictorial, where you've got your generator in the top left, and if you move in the direction from left to right, you're looking at essentially ascending powers of sigma, whereas if you move down, you're looking at ascending powers of p. And the point is that anything inside of this module can be written as a combination of these blocks, okay? When the module is free, there are no relations between these blocks. When the module is not free, we have some relation between these blocks. That's kind of the idea. So we'll see these pictures as we move forward. One thing that's also useful to know is that the bottom right-hand corner of this picture, where you have the p to the s minus first power, and you've applied sigma minus 1 as many times as you can, that turns out to be equivalent in the ring to the operation, which is apply the norm map from k down to f and whack it with the maximum number of powers of p. So that winds up being useful because it's connecting the sort of modular action that we're performing back to some arithmetic that's associated to the field by thinking about these norms. All right. So let's see if we can make sense of trying to study this problem. Let me tell you what things look like for J1. I already told you that things were nice when we looked at pth power classes. Let me try to make precise what I mean when I say that things are nice. So this is from a paper of Jan and John and I's from 2006. It says, when you look at pth power classes, they decompose as a cyclic module that's generated by some element that we call alpha, together with a direct sum of what I'm going to call free pieces. So what I mean is they're free over these quotients, all right? And so we get sort of this one cyclic thing and then a bunch of other things that are cyclic, but sort of cyclic and free. And let me tell you a little bit more about this element alpha, because in some ways alpha you can tell is the sort of the element in this decomposition that's doing something that's slightly different from everything else. We often call this the exceptional element. So this element alpha is minimal relative to the dimension of the module it generates, provided that it satisfies the condition that when you look at the norm of this element, you wind up finding an element which is a pth power in k, but which is not a pth power in f. And in fact, it turns out that when you look at the dimension of the module that's generated by this alpha, the math works out that you wind up getting back something that is one more than a power of p. So all these other pieces over here, these free pieces, they all have dimension which is exactly a power of p. And then this exceptional thing has dimension which is one more than a power of p. Okay. Again, one thing to take away from this decomposition when you see it is that the structure that we're seeing for pth power classes is far different and much more stratified than what you would expect to see from a generic module over this particular group ring. Because if in this case, so in the case of FPG, you actually can classify in decomposables. And it turns out that you get exactly p to the n many indecomposable types. So there are p to the n possibilities that could show up, so to speak, when you look at these terms.
Sorry,
But
what is n?
Say it again now?
What is n?
N is the base extension k over f, is Z mod P to the NZ.
Oh,
So it's
yeah,
keeping
right.
track essentially of how big the original tower is.
Okay. Oh, thank you.
Yep. So P to the N is the number of isomorphism types that in theory could appear. And you can see in this decomposition, we get N plus one of them actually appearing when we look at the decomposition per a particular field. And in fact, if you looked over all possible fields, it would be on the order of 2N possible isomorphism types. So, you know, roughly N of them showing up out of P to the N possibilities. There's a lot that doesn't show up. Things are really highly stratified. Now, of course, this is J1, where things are nice and the representation theory is on our side. So what happens when we try to go past this? Well, the good news when we try to get up to JS is that if you have elements that generate J1, then they will also generate JS because of Nakayama's lemma, basically, right? So in terms of finding elements that generate JS, we know exactly what to do. Just pick any decomposition that generated J1 and everything should be great. Of course, the problem is when you want a decomposition, you don't just want a collection of elements that span, you want an appropriate sense of independence. And this is what's hard, is that when you move into JS, keeping track of relations that appear at the level of JS that were not showing up at the level of JS minus one is then what becomes a little bit subtle. So to give you a sense of what this looks like, I want to draw a couple of pictures and see if we can think through some of the critical ideas. So I'm going to suppose that gamma generates a free R3G module. So in terms of the pictures that we've been doing, these are grids that go 3 steps down and then however many steps we want to go to the right. I've drawn it with 5 steps to the right. I guess I'm pretending that P is 5 and N is 1, but you can imagine you can draw even more interesting pictures. And I want to think about what would happen if it were the case that the corresponding module inside of J4 was not free, okay? So again, what would the module look like in J4? Well, it's one of these grids. Top left hand is just gamma's class inside of J4. But to say that the module that's being generated here is not free is the statement that there's some relationship or some relation between the cells in this grid. So just as an example, I've highlighted 3 of these cells here, and maybe we've got some relationship that says when I add the value up in each one of these cells, they wind up canceling out, right? So suppose we get some relation that looks like that. I hope you believe me that if I take a relation that looks like this, and if I just apply enough sigma minus 1s and powers of P, I can essentially push this relation so that it all sinks down into the bottom right-hand corner, right? And what it means is that that single bottom right-hand corner actually has to vanish. There's nothing in that corner, essentially, right? What does that mean from the perspective of J4? It means that if you look at P cubed times the norm, remember the bottom right corner was the highest power of P times the norm, it means that P cubed times the norm has to be a P to the 4th power. So we get something that looks like this. Of course, if I see an equation like that, I'm tempted to extract roots. And if I extract roots, of course, I lower the power of P that shows up everywhere, but I introduce one of these p-th roots of unity. So Kumar, here's the p-th roots of unity that you were asking about before, making, in fact, a very starring appearance, right? And of course, this equation here is telling me something about what happens in the bottom right-hand corner of the module generated by gamma inside of J3, right? So the point is that if the module generated by gamma inside of J4 is not going to be free, that's actually going to show up in a very specific way at the level of J3. Even if the module in J3 is free, that bottom right-hand corner has to have a very specific element inside of it in order for this kind of thing to show up. And the nice news is that this is more or less what happens in general. If I've got some collection of elements inside of the non-zero elements from K, and they've got some relationship inside of JS, that's what this combination is supposed to be representing, that they've got some non-trivial relation, then the idea is that if the things that are acting all happen to be divisible by P, I could just lower the power by P, and it introduces a p-th root of unity. So this dependence that shows up at the level of S gets manifested in terms of an equation that takes this form inside the level S minus 1. So again, if I want to find dependencies inside of JS, I really need to have good control over where the p-th root of unity lives inside of JS minus 1. And I'll just mention, in order to make this run, it turns out that this fact saying that P divides the sort of thing that's acting, it's really useful if you're looking at things that are free, or at least maybe free on the previous level, okay? All right, so this is in some ways going to be the thing that we're really trying to drive towards. Can we, in the language of COVID, can we quarantine where the p3 root of unity lives? If we can, it makes it much easier for us to understand the structure that we're trying to study. So let's see if we can do that in J1, right? This philosophy would say if we want to understand J2, we need to know where the p3 root of unity lives inside of J1. I already told you when we reviewed the decomposition for J1 from before that there's this magic element alpha that plays by a couple of rules. Its norm is a p to the power n k, but not a p to the power n f, and its dimension is this number p to the mu plus 1. Well, we prove a little lemma in that paper that says that if you pick up the element alpha that generates this exceptional summand inside of J1, then you can find field elements. So delta 0 is going to live in the intermediate field indexed by mu, and delta 1 is just some random thing. But the point is you're going to be able to find these field elements that satisfy these two equations at the same time. And I'll just say the first equation, that the action of sigma minus 1 on alpha produces delta naught times p times delta 1 to the p, really comes from the fact that the dimension of alpha is p to the mu plus 1. That's really the heart of that equation. Whereas the other equation, the fact that the norm is supposed to be a p to the power n k but not a p to the power n f, is the thing that makes this latter part true. That when I start studying norms, I wind up seeing a p3 root of unity showing up. Okay, I'm not pretending to have proved the lemma, but that's kind of where these ideas are coming from. But again, the important thing from this lemma is that you can see inside J1, we understand very well where this p3 root of unity lives. And that's really important as we try to uncover relations that show up inside of J2. Again, the exceptional element of J1 is kind of our key for understanding dependencies in J2. Now, the great news is that we don't have to stop there. Because if I got that relationship at the level of J1, of course, delta 1 hat is just some field element. And so I should be able to write delta 1 hat as some delta 1 times the p power class times some other thing. And then I can take that delta 2 hat and I can play the same game. It is something times a p power. So I could expand it like that. And if I keep doing it this way over and over and over again, eventually what I find is that sigma minus 1 times alpha is giving me this particular combination of sort of ascending powers of p times corresponding field elements. And then I get some residual piece that I won't see because I'm modding out by p to the s powers anyway. And so this is great because this alpha and these deltas then give us a toehold on where we can find a p3 root of unity. So if we're going to try to move up into these higher power classes and we want something to sort of be in charge of this notion of exceptionality that we had at the level of s equals 1, the natural thing to do is to try to find a minimal choice of alphas and deltas that satisfy this relationship. This is to say that they're all sort of coming from the alpha that we had originally. And also this relationship. And again, it might look like this is something new, but this is exactly the second part of the lemma from before, where I'm just taking advantage of the fact of how these deltas are related to each other. So in some sense, by sort of like Nakayamiing our way out of the definition for what alpha looked like at the level of J1, we naturally come to a place where we can try to do something similar to that now at the level of JS. So this is a great first swing at things. But as with a lot of good ideas, it needs a little bit of polishing. This is close to being right, but not quite right. And the reason it's not quite right is that alpha in this equation is only getting a chance to play a role here in the first part, but it's not getting a chance to play a role in where the p3 root of unity shows up. And so it turns out to make this thing run, you got to work a little bit harder. So here's the idea. We're going to define a norm pair to be a collection of indices from our fields and numbers that are congruent to 1 mod p that satisfy these two equations. So I need to be able to find field elements so that the ith field element lives in the corresponding intermediate field. So Kumar, you're asking about k minus infinity from before. This is why we want the k minus infinity, because some of these deltas I might be able to take as a 1. And if I can, I want to think about them as living inside this k minus infinity field. Okay. So the deltas live inside of these intermediate fields. instead of sigma minus 1 of alpha being this combination, instead I'm going to have sigma minus d of alpha. So the alpha is allowed to sort of intermix a little bit more freely. And likewise, when I look at the p root of unity and where it appears, not only do I have these norms of deltas showing up, but I also have this contribution that might be coming from alpha. None of the stuff you can see at the level of J1, because of course in J1, when I look at this element D, it's congruent to 1 mod P. It just looks like 1. But when you go past the J1 level and you can start seeing things mod P squared or mod P cubed, this is where this additional sort of integral combination, integral contribution of alpha can come in. So we're going to say a norm pair is minimal if it satisfies these conditions and there's not a smaller norm pair. And of course, that means I have to tell you what small means. Smallness is first and foremost lexicographic on where these elements live in terms of intermediate fields. We would like them to live in the smallest field possible from left to right. And furthermore, if I have two norm pairs and their A vectors match up, then I declare that D is less than D prime if I have some condition about just how close to 1 D and D prime are to each other. Again, I don't want you to get too bogged down in what this is supposed to be saying technically, but in essence, what I want to do is find the smallest solution to these equations, where smallness is preferenced from delta 0 and then moving forward after that. What's the hope if we do this? There's a lot of things to hope for. So one is that when I take these alphas and deltas and I mix them all together, remember, P, the pth root of unity, is in the module generated by these things. I would love for this module to be the module where that root of unity shows up. I would love it to be sort of in charge of quarantining relations, so to speak. So I want this to be indecomposable and a summand of my JS module. I would love to be able to actually compute the structure of this module. I would love that these elements are part of a nice generating set for J1. Remember, we already said that if you have a collection of things that sort of generate J1, they have to generate everything. So I want these elements to be the elements that show up in a decomposition for J1. And furthermore, I want them to show up paired off with other things that are also appropriately nice. What do I mean by appropriately nice? I mean that all the other things should be free and independent from each other. And finally, you can tell that we're obviously sketching an inductive argument here. We got to make sure that we can do all this stuff in such a way that it plays nice when you do induction, right? So we want to be able to sort of make sense of what it looks like to start at J1 and sort of climb the ladder all the way up to JS. So that's what we're gonna hope for. And I don't want to leave you in too much suspense. The hope is going to pay off.
Sorry, Andrew, so just could you go back to the previous slide?
Please, yes.
So as you vary S, you're building up, each time you're getting an indecomposable summand of the JS, there's some compatibility or something, presumably, you know?
That's right. Yeah, exactly. And this is this idea that I want all this stuff to play nice as I am inducting through these things. Because if I do it at one level and I want to move up to the next level, essentially the idea is that this module is going to suck up something from T, right? Every time T is going to lose something into that exceptional piece, or at least it has the potential to. In some ways, I suppose we would prefer not to have to do that according to this lexicographic ordering. But you're right that it's going to keep shuffling. The exceptional part's going to swallow up more and more as S gets bigger and bigger. Yep, on the nose, that's right. Okay, so that's kind of what the sketch is. Let me show you how some of this stuff works out. I'll say that this particular project ran about 3 papers long, and I think in total, Jan, what did we hit? Like 120 pages. So I won't do all the details. There's plenty to say, but I want to give you sort of the bird's eye view. So I said before that when you're building this thing, you want to do it in a minimal way. In the most spiritual sense possible, that minimality is because we want to make sure that we have not put anything extra into this module. Because if I had put extra stuff, the module would then maybe decompose into smaller pieces, right? I want to put in only what I need to make sure it gives me what I need, but then it doesn't break apart. So what are some of the things that come out of this minimality condition, other than the sort of like spiritual hope? Like, what are some actual concrete things we can prove? Well, one of the things that shows up is a monotonicity style lemma. And what it says is, if you've got a minimal norm pair, and you remember these A's are telling us the intermediate fields where the deltas are supposed to live. And the idea is, if you've got real deal deltas, so Kumar, this comes back to your K minus infinity question again. Some of the deltas could be 1. I'm just going to ignore those. But if I pick up 2 deltas that are not 1, they live in intermediate fields. And what this argument says is, as I move through my minimal norm pair, the elements have to be coming from higher and higher fields. It doesn't make sense to take an element from a high field in the 2nd slot and then an element from a smaller field in the 5th slot. That can't happen. And in fact, this is one of these things where the proof is not complicated, because you just pretend that for whatever reason this didn't happen. And what we're going to do is we're going to take the jth slot, and if AJ is less than or equal to AK, I can think of that delta as living in the same field as the delta K does. So what I'm going to do is I'm just going to fold delta J into delta K. And when I do that, I haven't moved where the kth slot lives, but I have now vacated the jth slot, right? I've made the jth slot a 1, which means that that's now a minus infinity. Of course, I have to pay for that by adjusting what the jth spot is, and all the other deltas work out. Well, if you look at what a minimal norm pair means for the original A's and their corresponding deltas, you get these 2 equations. But it turns out that the way that we've relabeled here means that you can just put hats everywhere, and the equations are still true. So it's still a norm pair. But again, critically, this relabeling has lowered where my jth term come from. It doesn't come from AJ anymore. It now comes from minus infinity, because I totally vacated that spot, right? So I found something smaller in kind of an easy way. This is the easiest of the arguments, but ideas that are more complicated, but certainly close kin to the one that I just wrote down, gives us a bunch of other results as well. So for example, we just argued that if K is less than J, then AK needs to be less than AJ. Well, in fact, you can say something even more precise. It turns out that that essentially the difference of AJ and AK needs to be bigger than the difference of J and K. So they can't grow like in a straight line. They can't grow like y equals x. They have to sort of sit above that line, right? So I'm thinking of this as saying that these elements are relatively big. When I say relatively big, I mean relative to each other, right? Somehow understanding where these positions are forces one number to be larger than another based on how far apart they are. It's also true that
inequality is strict, right? It's not less than or equal to.
It's strict. Yeah, exactly. Right.
Okay.
Yeah. There's another one that says, if you know exactly where D sits, so if D is congruent to 1 mod P of the T and not congruent to 1 mod higher powers, and we're still sort of in the universe that we're interested in, then if you have a term appearing, the field that it lives in has to be relatively high. So I'm saying this means that terms are eventually big. And as it's also true that the delta i's wind up having to be free. And as I've said before, this freeness is really useful for us. And there are several other things as well. There's about 6 or 7 conditions that we get, but these I think give a reasonable good flavor for what we're seeing. And I guess importantly, all these properties that we get from minimality wind up being really important when we want to understand what this module actually looks like. So let's see what we can say about this module. The good news is that this module indeed is a summand. So that's one of the things that we hoped, is that it really is sort of its own little corner of this decomposition. And indeed, these terms are a part of a basis for J1 that gives us a nice complete description of the P to the S power classes as this one exceptional thing plus a bunch of other things. So this is already kind of a big leg up when we're trying to break things apart. The key ingredients, we need a lot of stuff, but you certainly need to know where the P through divinity sits because of the important role it plays in discovering dependencies, and the freeness of the deltas winds up being a big deal too. We also, of course, wanted this module to be indecomposable, and we wanted to understand its isomorphism type. Good news, we can do that. It is indecomposable, and its isomorphism type is the one that we're writing down here. This is a proof that I can give you a sketch of. So the sketch goes like this. You should read our paper in the Journal of Algebra. This is about 40 pages. There's a lot of technicality that goes into this stuff. So it's not a simple thing to do. It takes quite a bit. You can imagine it's inductive in nature, but you really have to push hard on this thing to verify that it is indecomposable. Let me just show you what it looks like pictorially, though. I can't really tell you why it's indecomposable because we don't have time, but I can show you what it looks like. These are the generators and the relations. So I have these x's and I have this y. And this latter part, this latter relation tells us that the x's are all appropriately free. And this first part tells us how y is sort of intertwined with those x's. So let me just show you what the free pieces look like first. There's an x0, an x1, an x2, and x3. I'm just doing this in the case, I guess, when s is equal to 4. So I get pieces that look like this. And again, as I move further along, the terms get larger and larger because they come from higher and higher intermediate fields. I've color-coded some pieces and boxed certain terms here because those are the terms that show up on the right-hand side of this relation that we see here. And in fact, if you want to depict the relation, sigma minus dy sort of sits inside this box here. But the magic is that these other pieces are all sort of layered behind it as well, right? So this module has kind of a graphical depiction, but it's this layering effect of a bunch of boxes together with this kind of squiggly looking thing that's on the bottom, which is kind of cool. All right, what about everything else? I told you there's this T module. What about all the other pieces? The great news is that all those pieces are free. And why are they free? Well, if they weren't free, then the bottom right-hand corner of the sort of graphical depiction of the module they generate would be a p to the s power. And then we do what we did before, which is you just extract roots. But if you extract roots, you're going to get a pth root of unity potentially. But this t is set up to be in the part of the module that's away from the root of unity. And so this thing actually vanishes. This xcp is really just trivial. And so the p to the s minus second power is trivial as well. Which sort of inductively allows us to kind of reach a contradiction. This, by the way, is exactly why there are no relations between the elements of T as well. So all the stuff from T generates free pieces, and those free pieces are all independent from each other. So what do we get in total? What we get is that if you've got this thing that I was calling a minimal norm pair, then in fact you can decompose JS. You get this exceptional summand, and you get a bunch of free pieces. Again, notice that almost all of the summands are free, and all those free things, of course, are generated by just one element. This is not to be taken lightly because the modular representation theory makes no promise that modules should look nice. And essentially, all the summands here look about as pretty as you could hope they look. For a given field, of course, there are n+1 isomorphism types that show up from this stuff, and then we get the wackadoodle exceptional piece. And so there are most n+2 isomorphisms that show up for a given extension. But even if you look across all possible extensions, there are only so many isomorphism types for this exceptional module. So we really only get finitely many isomorphism types that are possible amongst all the k over f. And finite, of course, we could be very precise and say the number, but the point is here that there just aren't that many things that could potentially show up. And I guess if nothing else, I hope the thing that you take away from this is that the miracle here is that the module structure for JS turns out to be nice. This is not what you would expect if you were walking down an alley and an RSG module came up to you, right? Because most of these modules are horrific, but this one is actually nice. So it's nice enough that I think it deserves the celebration emoji and some extra decoration as well. So this is a really amazing thing that pops out of this. In the just few minutes that I have left, let me just give you a couple of final thoughts, some of which I've got answers for and some of which I think there are good answers for, but I haven't sat down to do it yet. One very natural question to ask is whether or not we can have a reasonable dictionary that lets us translate module theoretic properties inside of JS back to embedding style problems or Galois group computations inside of the field, right? So being able to do that would tell us how the nice structure that we're seeing for JS manifests in terms of some specific properties that Galois groups have to have. So this would be a very nice thing to answer. Another very natural question to ask is what does this decomposition mean? And in the decomposition, of course, there's the exceptional piece that has these two qualities attached to it. There's this vector of intermediate field information that we called A, and then there's this number D that are in charge of keeping track of the structure of what that module looks like. And then we got a bunch of free stuff as well. So what is the data of this exceptional piece actually doing for us? And the good news is that we've got solid answers for that. For D, again, I feel like I'm coming up on time, so I'll move a little faster. Kumar, this comes back to your other question about roots of unity. We're going to let p to the nu be the largest p power root of unity in the top field, and p to the omega will be the largest p-th power root of unity inside of the ground field. And the idea then is that if you are in a situation where omega is smaller than nu, which means that as you move up the tower, you pick up some new p-th power roots of unity, then it turns out if you've got a minimal norm pair that the D number is congruent to some other D hat, and the D and D hat are congruent to each other mod p to the nu, then you can prove that a D twiddle is also a minimal norm pair. And one way to think about this is that the D that you wind up getting is only defined up to the maximum p-th power of unity that shows up in the extension. Okay, so that's one piece of information that's important when you're keeping track of these roots of unity. They are keeping track of how much information you can try to squeeze out of this element D. If it turns out that omega and nu are the same, if we don't pick up new p-th power roots of unity along the way, then D has to be congruent to 1 mod p to the s. And these observations together can be sort of summarized in the fact that D winds up being equivalent to the cyclotomic character modulo, the minimum of those two numbers. So D in some sense is keeping track of how our Galois group is acting on the maximum p-th power of unity inside of the field. Kind of nice. The other invariant that we had is this vector A. And I want to tell you a little bit about what A is trying to represent. So to do that, I need to define a sequence of B's. So again, following the same notation that nu is the maximum p-th power root of unity inside of K, I'm going to declare B nu is going to be N. And then for everything smaller than that, basically what I'm going to be doing for BI is I'm going to be keeping track of where the next p-th power root of u shows up inside of the tower. So the case where BI is minus infinity, this is the first place where Cp to the I plus 1 could have been a norm, because it's the first intermediate field extension where that root of unity even exists in the bottom part of the extension. But if it doesn't show up the first place it could, I want to keep track of where it shows up above that. And that's what this minimum is keeping track of. So BI in some sense is keeping track of the first place where p to the I plus 1 shows up as a p-th power root of unity. The theorem is that the A's that we developed, these are the locations of the deltas that show up in our minimal norm pair. The A's are essentially the BI's as long as the BI's increase fast enough. And if the BI's don't increase fast enough, then the AI drops down to minus infinity. This is where we see this gap. And it turns out that you can connect this. There's an old theorem of Albert's that you can sort of turn on its head to find this result out. The idea is that this particular series of quantities are invested in trying to understand when certain embedding problems have solutions along the tower of K over F. Of course, along this tower, all of the extensions are p-th power cyclic groups. And we want to know when one of those things embeds in another p-th power cyclic group that jumps up by I plus 1. So these A's are keeping track of really some pretty explicit Galois theoretic information inside the field as well. I think, oh man, I can't believe it. That's it. And I think I finished on time. It's a miracle. Hooray. I need another celebration emoji.
It's perfect timing. Thank you, Andrew. Great.